Welcome. Our distinguished speaker today is our own Steve Seitz. Steve is a professor in our computer science and engineering department. He received his bachelor's degree from UC Berkeley and his PhD from the University of Wisconsin. And he was at Carnegie Mellon University for just 2 years as an assistant professor before he began the latest trend of the Western migration of faculty from Carnegie Mellon to UW. And Steve has received many awards, including the David Marr Prize for Best Paper in Computer Vision twice, not once but twice. And he's also received the ONR Young Investigator Award, the Career Award by NSF, and also the Sloan Fellowship. And Steve spent a couple of years at Google, and today he'll tell us about the fun things that he did when he was there. So, Steve.
All right. Thank you very much, Raj. Thank you all for inviting me. I should thank myself for inviting myself. So as Raj pointed out, I've been at, 2 years ago I started a new computer vision group at Google. They have a lab in Seattle, as many of you know. And this is really I think the first chance I've had to really tell you more about what we've been working on. And so I thought I'd do that. So just to get started, here's one of my favorite example scenes, Trevi Fountain in Rome. And so suppose that, first of all, this is, I think, a pretty impressive photo of Trevi Fountain. I downloaded it from Flickr a few days ago. And suppose that this was a simulation. Like suppose that we added motion to the water, and there was the smell of gelato, and it was much more realistic than this. So would this capture the sense of being at Trevi Fountain? So if the goal of the holodeck is to get the sense of being there, simulate the sense of being there, do we have hope to do this with Trevi Fountain? So how many of you have been to Trevi Fountain before? So about maybe a quarter of you. So does this capture your experience? Does this seem to you what Trevi Fountain was like? What's wrong with it? It's not wet, or it is. So there's no people, right? I mean, so I think to really get the experience of being there, you have to turn the camera around 180 degrees and see what people are there. So this is really the experience of being at Trevi Fountain, right? So the thing I love about this picture is that no one is actually looking at the fountain. So in fact, you'll see people here sitting at the edge of the fountain, looking back at the crowd. The fountain is in this direction, not that direction. People are playing with their cameras. It's sort of a hot day. So I mean, this is really the experience of being at the Trevi Fountain. So this really begs the question of what is the goal of this simulation? Do we want to simulate this, or do we want to simulate this? And I think this is actually a really hard question, which is pretty unresolved in computer graphics, which is, it's not sufficient to just capture the photons and literally kind of put you down in the scene and have you wander around. You want to think carefully about how you want to depict the scene. So do we want this sort of idealized scene, or do we want this really realistic scene? And I think it also depends on the goal of your visualization, why you're producing this visualization. So in particular, as I mentioned, I've been at Google for a couple of years, and in particular, working on the Maps division, Google Maps. And so really the question that my group is trying to answer is, one of the questions is, when you do a search for Trevi Fountain on the map, what should we present to you? How should we depict Trevi Fountain from this search? Okay, so this is more constrained, obviously, than this general kind of holodeck visualization grail, holy grail, because it's on Google Maps, and Google Maps has certain constraints, and people that use maps have certain expected behaviors. So, for example, so on maps, maps are really all about having spatial context, right? So you really need to understand where the scene relates to the rest of its environs, And if you're showing photos, it's really important that you understand, or that the user understands, how the photos relate to each other spatially. So it was really important that we capture that. The other thing, which is I think a bit more subtle, and I think we didn't fully appreciate it before we got to Google and started thinking about this, is it has to be fast. So generally people don't, I mean some people do, but generally people don't use maps for free-form exploration, right? It's very specific queries like, tell me how to get to point X from point Y, okay? And you want to answer really quickly, and so the visualization that we provide should also be really fast, relatively. So we don't have as, arbitrary amount of time to spend on this. It should be dead simple to navigate. So we shouldn't be producing a video game because really your grandmother should be able to navigate this. So there are a lot of grandmothers and grandfathers who use maps, and so it should be super simple and easy to navigate. It's also, like the holodeck, it should have some form of immersion. Like you should feel that you're in the scene rather than looking at a photo. And this is also pretty important. And then the last thing, as with anything at Google, it has to be scalable, right? So it can't just work for a handful of scenes. This should work for, ideally, any major site that you search for on Google. So how can you come up with an experience which will satisfy all of these things? That was really the challenge. And the answer that we came up with, which I think by no means is the final word on this, but I think it's a compelling start, is to create essentially a 3D movie. Okay, so why a 3D movie? Well, 3D movie can be as fast or slow as you want it to be. Just we can make it longer or slower by lengthening the size of the movie, and there's no controls for the user to have to figure out, so they don't spend any time messing with controls other than play and stop. So it's dead simple to navigate. It can be as quick as we want it to be. What I mean by 3D, well, I'll show you some demos shortly. But the key thing is that it's going to show a series of photos in spatial context, and we're going to show 3D transitions by physically moving the camera from the first viewpoint to the next. And so we'll give that spatial context, we'll make it immersive by adding 3D effects. And of course, it has to be scalable, and I'll talk about how we accomplish this last step. Okay, so this is sort of the justification for doing this movie. So what I'd like to do next is give you a demo of the product that we built. And this is, we just launched this about 2 weeks ago. So if you go to maps.google.com, you may notice this thing in the bottom called MapsGL enabled, so I'll talk more about that later. This is the newest version of Google Maps. If you're not in it, it will give you an option, and you have a machine which can run it. It will give you an option to opt in. So next time you run Google Maps, I encourage you to opt in and try this out. So if you go to maps.google.com/phototours, it takes you to this special side panel which is already opened and shows you some of the tours that the highlights of the tours that we've computed. So here are a bunch of tours. I'm just going to show you the first one. So I'll click on Trevi Fountain. And so what's going to happen is that it's going to basically load the map of Rome and then go into the inscription at the top of Trevi Fountain and slowly zoom out. And it's going from one user photo to the next. So you see these are from Panoramio and the name of the person who uploaded that photo. And it's kind of taking you around the Trevi Fountain, moving from one public, user-provided photo to the next. And you may see that there's kind of this parallax 3D effect, especially at the bottom, where we're computing 3D geometry from all these photos, and we're using that to render transitions from one to the next. And what's cool is you can see it at all times of day, because people take photos at all times of day, and nighttime photos as well, like this one. And then you get to see the crowd as well as the fountain. So it's showing you some of the context of the scene. And what's neat about this is that it's computing this tour automatically. Okay, so we're basically taking all the public photos of the Trevi Fountain that we have license to use. So these are photos that have been uploaded to Picasa Web or this other website called Panoramio. And we're doing a bunch of processing on these photos to automatically create these tours. Yes?
How many photos were used in that particular clip?
I can't remember the exact number, but like somewhere in the order of 10 to 20 maybe. But these tours range from 5 photos to about 40 photos for the longest ones. And it's proportional to how many photos we have. So for Notre Dame, Trevi Fountain, the Coliseum, you'll see longer tours because we have a lot more photos to choose from. Yes, Oren.
Is this technique susceptible to attacks where people would upload photographs with somebody holding, a banner saying, Yankee go home or something worse, and that'll find its way to the photo tour if it's computed automatically?
Right. So the question is it susceptible to spam, bad photos? We do have a process in place to get rid of spam photos.
My other question is, you're controlling the geometry, but what about the time of day? Is that something that you're controlling, or could it be like morning and suddenly pop into evening and back to morning?
Yeah, so what about time of day? We're intentionally leaving all times of day in here to just give variety, and if I play this again, you may notice there's a couple times where it actually did exactly what you said, where it started out during the morning and then went to a nighttime photo. So I think there are pros and cons. On one hand, it may seem weird, to suddenly go back and forth between night and day. On the other hand, we wanted to get the full variety of experiences of this scene. And I think there's various ways we could try to mitigate, get the best of both worlds, which we haven't explored yet. All right. Let's see. So to give you a sense of this, I think I'll let this one finish again. So there are a bunch of other features here. You can pause, etc. It shows you a next tour. You can also rate the tours, and I encourage you to rate the tours. Tell us the ones you like and don't like, so we can improve our algorithms. There's also the show nearby feature, and so if you click on that, it's showing you nearby tours in this vicinity. And actually, let me change to the map mode so it's a little bit easier to see. So here are the nearby photos near the Trevi Fountain, and if we zoom out, you'll see a bunch more in the larger area. So anyway, so there are roughly 100 or so tours in Rome, and you can keep zooming out and see all the tours in Italy, in various places, in Florence and Venice, and then in Europe. So this gives you a sense of the coverage. We have about 15,000 tours computed. And I want to talk a little bit about the history leading up to this, and then also more about how these tours are constructed, but to try to give you a bit more context. And I think many of you know a lot of this already, but I think it's still interesting to re-examine it. So this journey kind of started in 2005 when, at the time, this graduate student here, Noah Snavely, was working with me and Rick Salisky, and we started playing around with what you can do with photos on the internet, and on Flickr in particular, this web sharing site. And so we started typing in queries like Trevi Fountain on Flickr.com, downloading all the photos that were there at the time, and trying to match them together and to create 3D models. And this turned out to work far better than we expected. Here's a time-lapse reconstruction of Trevi Fountain from Noah's work. So Noah is now a professor at Cornell. This shows the Trevi Fountain being reconstructed from a set of photos. You can see the cameras are being added a few at a time, and then the point cloud kind of locks into place after a few iterations. Unfortunately, the algorithm isn't quite this fast, but we have newer versions that run on GPUs and so forth, which are starting to approach this speed. All right, so in the next year, this led to this cool system called phototourism that Noah developed, and it's really a way of browsing photos. This is just a clip from the SIGGRAPH video. So we're in Prague here, and just by clicking on different buttons or selecting photos, you can navigate through the scene. You can move, in this case, walk right down the scene, down the street, and people kind of fade in and fade out because the images were taken at different times by different people. But the background is consistent and presented in a geometric context. So this seemed like, to us, a fairly magical capability that you could suddenly take all these unrelated photos from the internet and then kind of tie them together in this 3D browsing scenario. So the next year, we, the background here was, so Rick Salisky was co-advising on this project. He's head of the vision group at Microsoft. And he was, of course, really excited about having this to be developed at Microsoft. And there were a number of developments at the time which enabled making this happen. One was Live Labs came about, and they had just acquired a company called Sea Dragon that had this great streaming technology for enabling images to be streamed across the internet, and then combining that with the 3D work of phototourism, they were able to create this thing called Photosynth. And so Photosynth basically lets you upload your own photos and create a visualization very similar to what I just showed you in the phototourism demo. While Photosynth was being developed, at Microsoft, we were also continuing research at the university. And one of the next things we wanted to do was to see whether we could scale this up to city scale. So instead of doing a tourist site like Trevi Fountain, we wanted to see if you could just type the word Rome on Flickr, download everyone's photos of the city of Rome, and reconstruct as much of the city as we could. And so this is work by Samir Agarwal. This is from the Rome in a Day project. And this actually isn't Rome. This is, turns out that Rome breaks up into lots of tiny pieces because people don't take photographs of every single thing in Rome. They just take photos of the highlights. What I'm showing you is Dubrovnik, which actually was reconstructed as one big chunk. And the reason is that it's on a hill, so you can climb up to the top of the hill and take photos from the top of the hill, and you get these panoramic views of the city, which helps stitch all the reconstructions together. And so when we ran our algorithm, we got this nice combined view of the city from the hillside, down to the rooftops, down to the ground. So now we're kind of in the main square, looking from camera viewpoints that are popularly taken in this city. And so each one of those little things here is one of the photos that was taken, one of the user photos on Flickr. So if you took a photo of Dubrovnik, a few years ago and uploaded it to Flickr, you're probably in this model somewhere. And it got the hillside behind and so forth. Another thing that we wanted to do was, you've noticed, I'm sure, that these models are very sparse. Basically, they're clouds of points. It's kind of like an impressionist model of the Colosseum. And the reason is that these are feature points which have been matched in the images, and we don't find features everywhere, and we're only reconstructing points in 3D where we find these features. And so what we wanted to do was see if we could get denser models. And there's another branch of computer vision called stereo, which is good at recovering dense models when you know where the cameras are. And so now we basically have this pipeline that takes the raw images, produces these sparse models, and tells you where the cameras are. That's called structure for motion. And then we take the output of this, which is camera positions, and we run these through stereo algorithms, and that gives you something which looks like this. And this is a much denser model, still a point cloud, but lots and lots more points. And it's much closer to what you would get if you laser scanned the Colosseum. And so this is essentially a laser scan of the Colosseum from people's vacation photos. And this is work by Yasu Furukawa, who's another postdoc who worked with me and Brian and Rick. And we also had another postdoc, Michael Gossela, who's now a professor in Germany, who also worked on a previous version of this. All right, so that's kind of the background. So this work, we were kind of getting more and more, pushing more and more towards scale as the city scale results showed you, and density and accuracy and so forth. And one of the things I noticed was it was actually getting harder to get papers published because we would write these papers and reviewers would say, oh, well, you're just building a big system. This isn't new computer vision. You're just scaling things up, right? And obviously there's a lot of complexity in, people who work in systems know that there's a lot of complexity to scale things up, but vision researchers generally don't know that or don't appreciate it as much as I wish they would. And at the same time, there was a lot of really interesting stuff happening in the industry, with photosynth and so forth. And so a couple of years ago, I had the opportunity to go to Google and start a group to kind of further push the limits in this area at Google. And so really the attraction was, for me, first of all, to create a new 3D computer vision team. So I had these amazing researchers like Samir and Yasu, and they're basically postdocs, and we're going to graduate and go somewhere else. So I was really excited to try to entice them to stay working with me and do even more exciting stuff on this new team. And we managed to recruit like a really fantastic 3D computer vision team. Certainly one of the best in the world. The other thing which was really exciting to me was to work on maps. And so, maps is one of the things I use most on the internet. And I really felt like there were opportunities to do things in maps with photos and imagery that didn't exist when we started this project. So, and I still think there's a lot more opportunities than even what we've done. So building the next generation version of Google Maps was extremely exciting to me. Okay, so that's kind of what was my motivation in doing this. And so the plan was I would take 2 years to go on leave, start up this computer vision group, and then come back to the university, and that's what's happened. So I'm now back at the university, spending part of my time at Google continuing to work with folks on this group. So let me tell you more about what we've done there. Now, so I guess I should say the first thing that was a challenge for us was, obviously we wanted to build the next generation of Google Maps to incorporate all sorts of wonderful 3D technology. The thing I didn't realize was Maps infrastructure does not support 3D rendering at all, right? So if you don't know much about Maps infrastructure, it's basically a set of tiles. So when you go to a map server, you get these image tiles. They're essentially raster images which have been rendered for you and then served to you. And as you pan around, you're pulling up new images. So there's no rendering, there's no fancy 3D, there's nothing. So basically the Maps infrastructure doesn't support doing 3D. So this is sort of a rude awakening for us. And we realized that in order to do anything like this, like 3D rendering and reconstruction and so forth, we'd have to basically throw out all the Maps infrastructure and rewrite it from scratch. And that's really what we did for the last year or so. Not just us, but working with other Maps teams in Seattle and Mountain View and other places. We basically rewrote Maps from scratch to support 3D. And that's this platform called MapsGL, which I demoed for you before. So this is really a version of Maps, which looks very similar to the existing version of Maps. But now it's using vectors, and it's using 3D rendering, and it's using modern graphics hardware and software. And so it now supports all the stuff that we would want to build on top of it. Yes?
How large is your team?
How large is my team? Well, so it's hard to answer because there's a set of teams. So we're really the 3D computer vision team, and we work closely with another client team. But on the people doing computer vision on my team, on the order of half dozen. So anyway, so this was the first thing that we did, and I think we spent more time than I would have liked to on the infrastructure of building this. But now that we have it, I think it's really a platform to do lots of exciting stuff going forward. All right, so let me tell you about I said that MapsGL looks very similar to the current version of Maps, but there are a few bells and whistles, some of which that we contributed on my team, and I want to tell you a little bit about those. So actually, why don't I just give you a quick demo of MapsGL. Okay, so we're in Seattle already. Why don't we go zoom into the University of Washington, and I'm just going to go to, let's do that. Here we are. So let's go to satellite view. Let's go down to the Allen Center.
You're going to show us how many cookies are left, right?
So okay, so now we're basically close to. So if you zoom into the next level, you will see. Okay, so there's the Allen Center. You might have seen there's this transition. Okay, it's from overhead view. Let me turn off the labels. It makes it a little bit easier to see. There's a transition from overhead view to kind of a 45 oblique view. And it's sort of subtle, but there's an animation here which kind of tilts up. And before, what this looked like is a complete change of context. So in order to get this tilt up effect, it turns out you have to have 3D geometry. So you can see this a little bit more when we rotate. So let's rotate to a different heading. Okay, so we've rotated 90 degrees. And the building is smoothly moving, in a way that it turns out in order to do this, you need to have a geometry model of the 3D model of the building so that you can create that very smooth transition. So it looks like a photograph, but it's using the underlying 3D to warp the pixels to create these smooth animations. So let's see. So the other thing, why don't we swoop down to Street View. So I believe there's Street View coverage here. So there you saw a little bit more of the 3D geometry that it's using. So anyway, so these are, I think they're subtle effects, but they enhance the visuals and make it significantly smoother and easier to use. So these are some of what we did for MapsGL, and let me show you, just briefly discuss some of the technology that went into that. So here's, this is not Seattle. I didn't have the 3D geometry of Seattle handy for this. This is Lausanne. So what we did is we took the aerial images of Lausanne from basically planes which kind of crisscross over the city. And from those photos, we constructed a 3D model of the terrain and the buildings. And here's what that 3D model looks like. So this is kind of a shaded rendering of the buildings. And so you can see, the outlines of buildings, and I guess I should use my mouse pointer to do this, and trees and so forth. And it's not super high resolution because we don't need super high fidelity models to do the kinds of effects I just described. We're not producing a 3D synthetic rendering. We're just trying to augment the photos. But it's enough to create these sorts of effects. So the way that this imagery is served is in terms of tiles, so for satellite imagery. So these little squares of pixels. And so for each one of these image tiles, what we're going to do is produce a depth tile, which is, it's as if the plane had a Kinect sensor, which was long range, and gave you distance for every pixel. And black is closer, white is further. And so from the model, we're creating these depth maps and serving these along with the imagery. And that's what's being used to warp the images as you move around. So turns out this is it builds upon recent work in multi-view stereo, which come out of the vision community, my group, and other groups over the last few years, 5 years or so. So this is really recent technology which enabled being able to do stuff like this. But still, there are lots of challenges to really make this work at scale. So, and I'm not going to go into detail on these, but very large separations between cameras as you move as you sweep back and forth over the sky. Very thin objects like telephone poles and wires and reflective surfaces. Water really messes up these algorithms. Windows are problematic, and it turns out there are a lot of windows in urban scenes. And maybe the most interesting one is non-perspective projection. And to really understand what I'm talking about, take a look at this. So You may have seen images like this on maps from time to time, and so this is LA. So this is so if you go to LA on maps, right, in Google Maps, you'll see an image which looks like this, and various other cities that have tall buildings. And the LA does not actually look quite like this. The buildings do not kind of tilt towards each other or separate in the middle like this. This one's kind of crazy. And so what's going on here is you can see that this is not a real perspective photo. This is a composite from multiple images. And somehow they're being combined to create this seemingly what looks like a photo, but it's not a real photo that anyone could have captured. It's a composite. So it's not a perspective image, and this poses a problem for us in 3D modeling because we have to produce a 3D model of this exact photo, right? So in order to get this rotation effect and zooming effect and so forth, the depth has to align perfectly with the pixels. So we have to make sure that our model is distorted as well. So we went through quite a bit of work to try to figure out how to create these non-perspective 3D models in order to sync them up with the imagery. So anyway, so there are a lot of interesting challenges in taking research ideas like stereo and actually putting them into production in a system like this. Yes? Why don't you fix the image? It's a good question. So the trick is that to fix the image, you would have to have really, really good geometry because you would have to basically produce a single, so these images, basically the plane is flying overhead and you're getting images taken from different perspectives and you're trying to create a composite, which is arbitrarily large field of view if you look at it on a big monitor. And so for these to stitch together, you would have to have really good 3D geometry to align them perfectly. So maybe we should have tried to get really perfect geometry, but that didn't seem feasible at the level that we thought we needed to fix the images. So it turns out that this is a worst case scenario. Most of the time, you don't notice it. I had to hunt and choose to find one which looked this bad. I think but still, we had to align it in order to make it work. This is from maps.google.com. You type in LA and.
Where did people take that picture? The different pictures that would make this up from ground level?
These are from planes. I want to talk about photo tours, it's the title of the talk, and this is as I mentioned, this feature that we just launched. And so this is really the first thing that, that we've been able to do subsequent to building this platform, and we're hoping to do a lot more beyond this. So this is kind of a cool story. This is a research project from my group here at UW, Avnish Kushal, grad student, working with me, and Ben Self, an undergrad. Working with other folks at Google and Brian Curlis here. And we basically co-advised this project to try to build these tours of famous scenes from collections of photos. And we've been working on this for a while at UW, and this basically turned into this project, inspired this project at Google. So here's some slides some images from the UW project. Here's a 3D model from point cloud of the Coliseum, and all these little cyan points are camera positions. So lots and lots of input photos of the Coliseum. And so the first observation is that while there are zillions of photos of the Coliseum, you don't actually have to see all of them. There's only a handful that you would really want to see, and you can find that handful by clustering these photos. So that's kind of the first thing that we did. We found popular viewpoints of the Coliseum by clustering these photos using and these are we call them canonical views, the photo clusters of the Coliseum, so the most popular viewpoints of the Coliseum. So our goal was, given these canonical views, to plan a path through this set of photos. And so essentially this is a graph traversal problem. If you think of these as cities, this is a form of the traveling salesman problem. We want to visit all of these views in the most efficient way. And we can define edge costs between them proportional to how well connected they are and how smooth the rendering is in other terms. Okay? So this can be reduced to a form of the traveling salesman problem. So here's the path. And first of all, we used this work by Ian Simon, which is another of my grad students here, now at Microsoft, to find these canonical views. And so here's the tour that we computed. And so what you'll see is that in addition to these circle views, there are also these in-between views. So from this photo to the next one, there are 3 in-between photos. And the reason is that the canonical views are not necessarily connected. They're the most popular views, but they may not be physically connected to each other. They don't overlap. And so we have to find other views in between that connect the two so that you can create a smooth transition. So we're finding these intermediate views as well as planning the path through the canonical views. Okay, so here's the output of Avanish and Ben's system. So this is the UW system, which produced these automatic tours of the Colosseum. And so it starts out when here, you see faces appear, disappear. At some point, it's going to go inside. It's rather abrupt, but these 2 photos apparently did overlap. And you get a tour of the inside as well. So anyway, so the Google version was inspired by this project. I think what I'll do is I'll show you some of the tours that I think are most interesting and demonstrate various attributes of this tour process. So, and again, these tours are, in our case, they're created automatically from public Picasa and Panoramio photos. So if you have photos on Picasa and you make them public, they may show up in these tours. This is in Florence. This is a cathedral in Florence. And so you're seeing this beautiful door. And so we're outside, and it's gonna go to the statue because people take photos of the statue as well. Now it's going inside the cathedral, and it's focusing on this amazing ceiling mosaic, and kind of rotating around it, and then zooming in on one figure in particular. So this one was cool because I like the combination of the inside and outside, and you sort of see. Really what this is capturing is the things that people think are most interesting. It's not capturing every single nook and cranny in the cathedral. It's capturing the things that people take most photos of. Yes?
So I would have thought the inside and the outside photos would have been disconnected. How did the system get those together?
So we have a mechanism for identifying that they're photos of the same place based on tags and a few other signals.
At this point in time, users navigate on their own path. Is that because of computation issues?
So the question is, can the user navigate on, or can't the user navigate on a path? So for this version, we decided we first wanted to get something out which did it completely automatically, and so sort of lean back and show me the thing. In the future, we're very interested in adding, interaction on top of that. But sort of the guiding philosophy is we want it to be quick and fast and easy and just briefly summarize what the experience is. And if you want to navigate, you can, but you don't have to. Yes?
So as a person who was watching this for the first time, I hadn't seen this, I would have expected to see a full view of the building in question and then zoom into the door and zoom into the other internal parts. But starting from a very localized position and moving very locally, I don't get a full picture of what the kind of place we are seeing. So if you could put in more knowledge, some kind of an AI knowledge of what are good tours or what are good typical tour descriptions, we might be able to.
Yes. So the question is, why don't we start with a big sort of panoramic view first and then zoom in rather than the opposite, which I think many of these tours are doing. And I think that's an excellent point. And we'd also observed that. I think the algorithm just has a tendency to go from one extreme end to the other. That's what the nature of the traveling salesman algorithm will do. And so often these panoramic views are not endpoints. They're kind of intermediate points. And so, for example, if you start with a panoramic view of Trevi, you might have to go left and then come back to your original view and then go right. And so it results in a less efficient tour. But that's a trade-off. Maybe it's worth it. It's a good point. So here's another one which I like for different reasons. This one really shows off the 3D. So here's the Arch of Titus in Rome. And you see a lot of the parallax and 3D geometry that we're computing. So it doesn't always work this well, but there are many examples like this where having that extra 3D really makes it feel immersive. This is a waterfall in Idaho. For some reason, it does really well with waterfalls. I didn't expect it to because they're hard to model in 3D. But you see the change in seasons. The water flow varies. It's less water flow during this season and dries up further over time. So you're able to stabilize the fall and get these dramatic changes over time in seasons. And this is something that I think would be hard to get without this kind of crowdsourced imagery capturing many different views and seasons and so forth. And again, it sort of mystifies me why it's able to create decent 3D geometry for waterfalls, because it breaks all the assumptions of computer vision assumptions that we're working with. So here's another one. This is this crazy, this is a water park. And what's kind of fun here is the background is static, but the foreground is changing in every image. So it's almost like you're seeing this dolphin show elapse. And their image is taken by different people on different days and so forth. But they sort of combine to give you this dolphin show. We're already in Seattle, so let's go to the Fremont Troll, one of our favorite local landmarks. So here's the Troll tour. This one we kind of hijacked. We took our own photos of the troll. And so you'll see one, which is the team. You may notice some familiar faces. So first it's showing you the plaque. So here we are. Disappeared. So in general, these photos are drawn from everyone's photos, but in this case, we just took it for our photos, created it from our photos specifically. All right. So I also want to give a plug for this thing called the Ceres solver. This is a nonlinear least squares solver, very general purpose nonlinear least squares solver, which really powers much of the technology that I've showed you today, as well as parts of Street View, and it's used all over in Google now. This is written by Samir Agarwal, who's affiliate faculty here, and Keir Meyerly. And so they've decided they want to open source this, and so they just released it a week or two ago, and you can go to this webpage to find out more details, but it's general purpose nonlinear least squares solver, works on all sorts of platforms, phone as well as PCs, open threaded, parallel, et cetera. So, and I feel like this is an exciting example of the potential for giving back. I think I've talked about a lot of examples here where we've taken research ideas from UW and elsewhere and built products out of them. But I'm really excited and committed to the idea of giving back to the community and feeding into the next generation of research. And just to close on that, one of my goals here was this magnification effect, which I think we got out of photosynth. So photosynth for my group was really terrific because it was a research project, but it turned into a product without a lot of work on our part. And brought all sorts of great things with it. You know, it brought publicity, students, funding, and users. And so I wanted to see whether if I could replicate that with many other projects. And I think to some extent we've had some success with that. So another example is Picasa face movies, which Iro Kemmelmacher developed. She's in the audience here, and she gave a colloque on this earlier this quarter, so I didn't want to talk about it today. But this is another example of a project from our group that turned into a feature of Picasa. The 3D technology in MapsGL and photo tours, again, came from the group. And then going the other way is the Sarah solver, and lots of folks in the group at Google come here and co-advise graduate students, and we're sharing data and code and so forth. So I'm really excited about sort of flow in both directions and want to keep going. So thank you very much.
Do we have time for some questions? Pedro.
Why don't you use A/B testing to figure out online what are the tours that people like most?
So how are we testing to find the tours that people like most? So, so we have this rating mechanism, this thumbs up, thumbs down. And so that gives us one signal. And so we're accumulating statistics from that. Yes, and so we have various metrics that we're collecting to try to get signals on these tours. But if you have other ideas, I'd love to hear them. Yes?
Can you say a little bit about what demands you make on your laptop there? I mean, do you need to be running Chrome? What kind of bandwidth do you need? Are you using any graphics accelerators, anything like that? Yeah,
so this is a MacBook Air, so it's not one of the most heavily powered machines, but it has a decent enough graphics card. So to run MapsGL, you have to have a relatively modern machine, although it works fine on some 2-3-year-old machines, but it has to have a decent graphics card. Right now it runs on Chrome and Firefox, and I think some versions of Safari. I think you have to enable like a special mode of Safari. Not Internet Explorer yet. They're not supporting WebGL yet, but I really hope they will. Does that answer the question?
How much data do you ship over?
How much data do we ship over? Well, so basically for the tours are relatively forgiving because where you see a new image about once every second or second and a half. And so we have a whole second and a half to download the next image at the resolution of the viewport, and we'll figure out what your resolution is. And so it's relatively, for me, it keeps up fine on almost everywhere I've used it, but it won't work on really slow networks. But there's definitely a bandwidth issue. I mean, for doing this, high bandwidth, photosynth-like stuff, if you're streaming lots of images, you have to design it in such a way that you can produce a compelling experience. And I think that was one of the motivations for why we did it this way. Linda.
The tours seem a bit short and limited to single buildings or single places. I wonder, is that a limit that you can't start at one end of Via del Corso and go all the way down to the other end? That I think there are landmarks at both ends and things in the middle and so on.
Yeah, so one question is the tours are short. The other one is, can you link them together? So the tours are short intentionally because we wanted to tailor it to maps where browsing sessions are typically short and people generally don't want to spend a lot of time. But I do agree that it would be great to be able to link things together, and to some extent we've done this. So at the bottom of the tour there's a next tour feature, and so you can always click on next tour, next tour, next tour. Although it is sort of a random walk, it's not necessarily getting you, it wouldn't do what you're asking for, which is show me all the tours along this route. And so that would be a cool feature to try to provide. But I do agree with you that, I'd love to be able to do a tour of a whole city, for example, and sort of give you a summary of Rome or Venice and have it sort of jump from one place to another in a reasonable direction.
So with photosynth, you really took photos in order to build a reconstruction. What you're doing at Google, it seems like more you're finding photos in order to do this for other people. And so do you think the kind of Microsoft photosynth model is not successful in a long-term sense, or do people not want to do that, or is that something?
So the question was, so photosynth, to create a photosynth, you had to take a set of photos yourself and upload them. Whereas here, we're just finding photos which already exist and combining them together. So I think I think both are plausible. If you're actively capturing photos, there are certain things you can do that are hard to do otherwise. So for example, we don't have a complete model of the Pantheon because almost no one takes photos of the back of the Pantheon. But if you're using photosynth, you can, or a program like it, you can just create whatever photos you want. If your goal is to model the Pantheon, you just simply walk all the way around and you can get a complete model. So I think that's a really compelling model. I mean, I think the work that Kathleen Tweet and Zoran have been doing here on PhotoCity is another example of that, if you can try to motivate people to take more photos. So I think there are pros and cons. I do believe that sort of crowdsourcing the photo collection is extremely powerful, and there are things that you can do with that you can't do from a single user taking photos, like getting the full variety of the scene, like the day versus night, different seasons and so forth is one thing. The other thing which is really powerful is figuring out what are the interesting views to show, right? And so most views of the Pantheon are probably really boring, right? It's just like some random little square on the wall. If you just sampled the light field of the Pantheon, you would get the average photo would not be interesting. So what you are interested in is the photos that people take over and over and over again. That you can really only get from this crowdsourced collection mechanism.
Okay, so let's thank the speaker again.